All right. Good day, folks. I believe there might have been some audio issue on the video there, but just the official session will be starting here in a few moments. Let me see here. All right. So for those of you on the line, we will just wait a couple more minutes for folks to join in for the official session. A couple housekeeping items just before we get started. Today's session will be recorded and available as a playback. So if there are folks that might not have been able to make it, or if you wanted to share this with some members of your team, please feel free to do so after the session is completed. There will also be a Q&A session at the end of today's session. There is a Q&A feature on this platform. So if you do have any questions as it relates to the content, maybe something related to you're working on, please feel free to post those in the chat. All right. Now that being said, I think, we're about a minute past the hour, so let's go into it here. All right, so good day, everyone, and welcome to today's webinar titled the ATH Functional Fillers for Thermally Conductive Adhesive Applications. Today, I'm happy to present two guest speakers. First, Pierre-Guillaume Colmard, Applications Engineer from Alteo, will be joining us, as well as Pankaj Yadav, Commercial Engineer at Metravib. So throughout today's session, we'll have a few different speakers covering some topics in this application space. So just to go over a little bit of an agenda for today, we'll start with some introductions. I myself will be giving us a brief overview on thermal conductivity and the Trident instrument from C-Therm side. Next, we'll be joined for a DMA application and fundamental review with Pankaj. And then at the end, and really the main topic here today will be to go over the ATH functional fillers review with Pierre. And he will also be discussing some of the results on the thermally conductive adhesives, both from the thermal conductivity side, as well as the mechanical side from DMA. And then, as mentioned, we'll be wrapping up with a Q&A session, so definitely feel free to stick around for that if you have any questions. All right, so I'll start with just a quick introduction to C-Therm Technologies. For those who may be new to us, wanted to just let you know who we are and what we do. So C-Therm, we are experts in thermal conductivity characterization, really focusing in on the transient class of measurement technique. Globally distributed, we have customers all across the world covering a range of applications. And really, in all cases, our goal and what we try to do is to simplify thermal conductivity testing for the materials of tomorrow. And again, this is all done through the transient class of measurement technique. And this has really culminated into our current platform, which is called Trident. So Trident, this is one instrument with multiple methods available for thermal conductivity characterization. Depending on the application, the sample, your testing conditions, one or the other of these methods may be more appropriate. You can see the 4 options listed here. Now, in today's session, and really what we'll be focusing on in related to today's work is the MTPS, which stands for the Modified Transient Plane Source. But I'll go into that in a little bit more detail here going forward. So ultimately, the idea with Trident and the reason why you want to have different options is to really make sure you're using the best tool for the task at hand. This really kind of is embodied in this quote, when all you have is a hammer, everything looks like a nail. This is a famous quote from Abraham Maslow. And really, this was the idea behind Trident. One of the biggest areas or biggest sources of poor data that we see is when you try to take a really good method but apply it on a material or a condition that it just really wasn't designed for. So again, really giving you that toolbox approach with Trident here to be able to pick the best tool for the task at hand. Now, for those of you who may be new to thermal conductivity or maybe just looking to learn and expand your knowledge on some of the different options out there, we do have a method selection guide available as a free resource on our website. You can certainly take advantage of that, take a look. It really covers all of the transient methods that we work with here at C-Therm, as well as some of the other methods that are available in industry, and really gives you some ideas on, which methods are best for maybe your specific application, and discusses some of the requirements and some of the theory behind some of those options. Now, of course, we are happy to, go through this with you. We offer a technical consultation service. This is a free of charge option where you can come and meet with us one-on-one, talk about your different applications, your testing goals. Certainly feel free to reach out to us if that's something you would like to pursue. We can also show you a system demonstration, kind of taking a sample, walking you through the steps and trying to show you how that would work on your application and your materials. And of course, if you are interested in pursuing this, certainly we do have a request a quote option as well, if this is something you'd be interested in pursuing further. And I do just want to highlight, so C-Therm Technologies, we are partnered with both Rigaku for their line of thermal analysis products, as well as Metravib for their DMAs. So C-Therm, we focus on thermal conductivity, but there are, of course, other material properties of interest, especially as it relates to some of these sample types. So if you are looking to expand on really the scope of your testing needs, definitely feel free to reach out and we can assist in either scenario. And also our thermal analysis labs. This is our contract testing division here at C-Therm. It's a full test facility with all of these options available. So maybe if you just were looking to get some samples tested, you didn't need to maybe get a full instrument, but you needed some data collection, we can certainly assist with that as well. And I wanted to end here on just a client testimonial. We always like to, share what our clients are saying about us. So this one here, I chose we purchased the C-Therm thermal conductivity analyzer, noticing how fast and easy it was to operate. The instrument provides unequivocal results and provides flexibility to test powders and liquids. In terms of our satisfaction, I give it a 10 out of 10. Always like to hear happy customers, what they have to say. This was Dr. Enrique Jackson from NASA. Okay, so now this brings me to really maybe more of the core of today's presentation from C-Therm side. I wanted to introduce the topic briefly here, as well as go over some of the aspects of the MTPS testing capabilities. So when we're looking at these types of thermal adhesives, these thermal compounds, these could be broadly categorized under the thermal interface material group. TIMs are essentially a material type that are there to help improve the heat transfer in a system between different components. You can see there's a variety of options here, depending on the type of sample that you're looking at, but these would all kind of fall under that larger umbrella of thermal interface materials. Now, as you can see with the TIM, again, they are placed between different components to really help improve that heat transfer. Generally, you have a heat generating component, something in an electronic system as an example, that's heating up during operation. And then there's a cooling system. But to really bridge those two and make sure that heat transfer is very efficient, these materials are placed in between to help accommodate this. Now, when we're looking at TIMs, regardless of which necessarily format they're in, thermal conductivity is viewed as a critical performance metric for these materials. This is something that we've seen time and time again, where thermal conductivity really plays an important role in the development of these samples, as well as the use cases, depending on what type of power heat dissipation is required. But really, and again, kind of related to what we'll be talking about later here today is the fillers. Now, fillers are going to be what's doing the majority of that heavy lifting within these thermal interface materials. They are the main additive that are used to help tailor the specific performance of interest. And this is what, of course, we'll go into a little bit here today with the ATH functional fillers. But when we talk about thermal conductivity here, and again, maybe some review for many, but if, again, folks that might be new to the topic, just wanted to give you the quick rundown. Thermal conductivity essentially describes a material's ability to conduct heat. This is an intrinsic material property, meaning it's independent of the size or the shape of the material that you're working with. In all the results and content presented here today, we will be referring to these SI units, thermal conductivity, watts per meter Kelvin. So this brings me to the MTPS. Again, this was the method that was used to characterize the samples that Pierre will be discussing a little later on in the session here today. So I wanted to just give a quick rundown on the MTPS and describe, what it is, what it can do, and a little bit on how it works. So you can see a picture of the sensor here. So this is the MTPS. It's a single-sided sensor design. Provides a measurement of thermal conductivity as well as thermal effusivity, which is another related property here. And noting here fast test times. It's about 1 to 3 seconds in duration to obtain a measurement. When we're looking at any transient technique, really any of the ones that we offer on Trident, transient will always be faster than your more traditional steady state options. But even amongst the transient methods that are available, the MTPS does rank as one of the fastest. So really great if you're in an R&D environment, you have a lot of samples you need to get through at a given time period. It really helps accommodate a high workload, expediting that sample throughput capability. Wanted to also just flag the versatility of the sensor here. It is one that can be used for testing the solids, but also liquids, powders, and pastes. When we're talking about thermal interface materials in particular, this can be really useful because whether you're looking to characterize the end product in its solid form, some of these materials come in an uncured state, more of a paste format. Depending on what you're looking to do, you can really test all of that. Even the powder, the fillers that you're looking to test, some groups do opt to test the fillers independently, just by themselves. Others, and what we'll be looking at here today, is where they're actually incorporated into a material and seeing how that changes based on loading. But in all scenarios, the MTPS is I call it a workhorse style sensor that can really accommodate quite a wide variety of testing capabilities. So from a principles of operations standpoint, just to give you an idea of how the sensor works, this is going to be a very high level rundown here, but essentially your sensor, the top side, there's a spiral heating element. This is what's essentially acting as the heat source. It's delivering that thermal energy for the test. Your sample is, of course, placed over top of the sensor. And then when you initiate the measurement, what we're doing is monitoring the change in temperature that occurs as a function of time. Now, of course, depending on the type of material you're testing, the conductivity range that it's in, whether it's more insulative or conductive, the extent of that temperature change will be quite different. But that is essentially what is used to determine your thermal properties of the material, the rate of change during your measurement. Now, with the MTPS, the nice thing with this measurement option is that all of the settings for your measurement, as well as the data analysis that occurs, this is all handled automatically by the software based on the calibration settings that are used. So it's a calibrated technique. And again, depending on if you're testing something more insulative, more conductive, there are some different options that you can pick from. But essentially, it really simplifies the testing approach. It's one option that we see really useful, especially if you have multiple folks in the lab that are all running with, running their samples with the instrument. It really cuts down on potential user bias because, again, once you place your sample on there and click go, everything from that point on is handled by the system. So, I'll leave that there. If you wanted to learn maybe a little bit more about the MTPS, if that was of interest, definitely feel free to reach out and we can discuss that further one-on-one. Now, kind of before I close out here, I just wanted to give two quick examples. As I mentioned, when we're looking at fillers, oftentimes, these are incorporated into some system to help tailor your performance. And of course, at different loading levels, different filler types, you can see you can obtain different types of thermal conductivity metrics for your samples. One thing that can happen though, when you're dealing with adding a filler into a material is what we're kind of showing on this image here. If the material, that filler does not inherently disperse itself evenly and uniformly within the material, what you can get is some issues with the uniformity and the heat dissipation. Now, this example here is quite exaggerated, but just to show the point here, there is a conductive filler added into this polymer matrix, very non-uniform. You can tell that just by looking at it, right? But one of the unique things with the MTPS related to the fact that it's a single-sided interface is we can actually take the sensor and move it around to different locations on your material, again, if you're dealing with a larger sample there, and do these spot measurements. And what this can really do is thermally map your sample and understand the consistency, or in this example, the lack thereof, of that thermal conductivity performance. So you can see here, the top left quadrant, based on this test location here, coming in about 0.35 watts per meter Kelvin. Again, and we can see that, fairly low based on the fact that it's very minimal fillers present in that test area. Whereas if you move over to spot number 3 here, we get a value almost 3 times higher. So in this example, this would be a really clear case where whether that was the process that was involved, whether the mixing, the curing, where the end product is certainly having some issues. This is just, of course, one example, but it really gives you the ability to understand how that uniformity is in your material. And the reason why we want to make sure your sample is uniform is because if this is applied in a system where there's heat being generated and we need to dissipate that heat, if you have something inherently variable like this, what you're going to get is potentially hot spot buildups, decreases in performance, and in some worse cases, some safety issues with things like thermal runaway. All right, but that brings me to the end of our introduction from C-Therm side. Just wanted to give you a little bit of a taste of some of the options there and kind of highlight the MTPS. At this point, I will go ahead and stop sharing my slides here and invite Pankaj to come on and talk a little bit about Metravib side of things. Thank you, everyone.
Thank you, Pierre and Arya, for the opportunity of presenting Metravib material testing. Hello, everyone. I'm Pankaj, and I'm working with Metravib material testing since over an year now as a commercial engineer. So I'm here to provide you a small insight on the Metravib material testing and on the DMA technology. So Metravib material testing is a French, it's a French DMA manufacturer company with an experience of over 50 years in the technology. So how it all started, it was in 1968 that we have started manufacturing DMAs, this technology, with a submarine acoustic contract. And here we are in 2024, where this technology has evolved in close collaboration or coordination with the industrial and the university partners and clients. So the question raises, what is DMA and what is its working principle? So DMA stands for Dynamic Mechanical Analyzer. It's a precision technique which helps someone who is interested in analyzing or to study the performance of their materials. to be more precise, the materials which are viscoelastic in nature. So as you can see the cross-section of the Metravib DMA here, the electrodynamic shaker applies the displacement or the force to the specimen as asked by the operator, and the resulting force or the displacement of the specimen is measured on the other hand, where these two signals have a phase angle. That means when we apply a small load or a displacement and the response of the material is measured, there is a delay in getting that response, which is denoted by an angle called as delta, or the tangent delta, which is also known as the phase angle. So what happens later on is these displacement and force signals are processed, that is integrated in the software itself, and it provides us the stiffness of the specimen, and hence the complex modulus and the tangent delta of the viscoelastic materials. So to provide you a small insight how these materials are tested, there can be different solicitation modes depending on what is the specimen shape and the characteristics. So we can test or we can analyze the performance of the material in tension mode. We can do in compression mode as well, in shear and in bending, depending on the, again, I'll precise it, depending on the morphology or the shape of the specimen. So here it's a small, it's let's say more or less, it is a classical DMA data where a material is analyzed to study what is the glassy region of the material and what is the rubbery plateau of, or the rubbery region of the material. Whereas we can also see in the graph that the transition region can be followed in the material depending on the temperatures or the environment that has been assigned to the temperature, or we can say that the material will be used in what sort of applications. So this was a quick background of the DMA and the Metravib material testing. Here are certain clients all over the world that are taking advantage of Metravib DMAs. So in case if you have any questions regarding it, please feel free to ask it later. Thank you so much. And I'll hand it over now to Arya.
So hello, everyone. Thank you for attending this webinar. I'm Pierre-Guillaume Colmard. I'm a material engineer, and I have over 10 years of past experience in epoxy and PU formulation. And I joined Alteo in 2019, so almost 5 years now. And I'm gonna present you our new product called TIMal M3, which could be used for thermally conductive adhesive applications. So I'm gonna start with a small company introduction. So Alteo is a French producer of ATH, so aluminium hydroxide and aluminum oxide, and it has today 130 years. It is 130 years old. So old company which was part in the past of Péchinet Group. Then it became Alcan, and after that Rio Tinto Alcan, to finally became Alteo. So we are located in south of France, between Aix-en-Provence and Marseille, in the Provence area. It has been the first Bayer process, by the way, which has been created in the world for bauxite refining to produce ATH. And since 2021, we have been acquired by a UMSI group, which is an international group specialized in mining logistics. So today we have a worldwide presence. So the headquarters, the R&D, and the calcination and milling facilities are based in France, south of France, as I explained before. And we also have some milling facilities in South Korea, Taiwan, in China via a joint venture. And we also plan to open a new milling facility in the US to address the North American markets. So we have around 200 million euros of turnover, and we are serving almost 700 customers. And we have dedicated application lab located in France. So here you can have a look at the different market Alteo is targeting, because in the past we were a producer of smelter grade alumina to produce aluminum, but now we decided to focus on specialty aluminas, which stands for high-end markets. So we have automotive markets with special attention to batteries application, both inside and outside the cell, as you will see later. We have also aeronautics, defense and space, and IoT, which is a very popular topic with semiconductors, for which we have to take care of a very high quality product with very low impurity levels. And the last market is energy and transportation also. So just to briefly introduce the process to produce aluminum oxide and ATH. So the feedstock, today we do not refine the bauxite anymore. So because of real estate pressure and urbanization in the Provence area. So our feedstock is aluminium hydroxide. Then we have a very unique and special dissolution and reprecipitation process. So that enables to get very low impurities and to have a specific radial structure. So we have a special product for that, which is the TIMal H, which has a roundish shape of around 100 microns. And then there is two options. We can either grind the product to get a different level of fineness for ATH, for thermal conductivity application or flame retardant applications. And the other option is a calcination step, where water will be evaporated at a very high temperature. We have a huge rotary kiln of around 100 meters long and 5 meters of diameter. And then it could be ground also down to very fine particle, down to 0.3 microns. So today we are specialized and we have different grinding capacities with continuous batch ball milling, wet milling, and airjet milling. So we are able to play and to pay a particular attention, especially on the coarse particle and the top cuts. So as I said, I work at the application lab, which belongs to ITech, which is the Innovation and Technical Excellence Center. We do have some technical experts for each market Alteo is targeting. So you've got a real brand for refractory applications. We have technical ceramics with high-cal product, and the two other divisions are functional fillers, for which I am in charge for TIMal product. So let's say outside the cell application, where you will see after the application, but it's related to flame retardancy and heat dissipation. And the last one is lithium-ion batteries for everything inside the cells. So for example, separator coating or also electrode could be used with our alumina powders manufactured here. So just to quickly introduce a TIMal range for EV application. First, on the right-hand side, you can see the different type of product which involve functional fillers to enhance the thermal conductivity. Because as you can see on the scale on the left, hair and also most of the polymers have a very low thermal conductivity. For example, it's in between 0.2 and 0.3 for most of the polymers. And once you want to dissipate the heat generated by the cells and the battery, then you have to look at some functional fillers, either oxide or metals. And the first choice comes if you are looking for electrically conductive or insulating materials. So ATH and aluminum oxide are within the range here between 10 and 300. So at Alteo, we do have a strong powder expertise. So we are able to work on the PSD of the powder. We can also work on the particle shape. This will bring a lower viscosity product with a lower specific surface area. We have also expertise on packing optimization to optimize and increase the filler content. And we also are able to offer for the whole TIMal range a filler treatment. So this will lead to a better matrix affinity, thus lowering the viscosity, and it can also bring some benefits in terms of sedimentation for shelf life when you want to be sure that your product won't exhibit sedimentation versus time. And we can also provide guidelines between our fillers or our fillers and other to meet your requirements in terms of thermal conductivity and viscosity. So usually via NDA, we are able to work either with a standard binder like a PU, epoxy, silicone, or we can also make some cross tests based on your binders if you are okay to send them to us. So we can study both rheological properties and thermal conductivity also. So when you look at the different key parameters listed on the right, you can see that density has a major importance for EVs today, cost competitive product also, low abrasivity, because for dispensing machine could be sometimes an issue, flame retardancy, thermal conductivity for sure, and mechanical properties is also of importance for adhesives. So that's why we have decided to launch this new product. So on the top right-hand side, you see that when the battery is heating, you need to dissipate the heat to the cooling plate, and to do such, the polymer is filled with functional fillers. And in order to optimize the capacity, you can clearly see some benefits by using different particles. So that's why you can see, for example, here, coarse, medium, and fine particle, just to optimize the capacity and to make some efficient pathway to dissipate the heat. So on the left, you can see a SEM picture of our product, including different size of particles. And at the bottom, you can see some example of hydrophobic surface treatment, which provide a nice lotus effect when we just put a drop of water into a pressed powder. So our product is a multimodal ATH. So it has an intrinsic bulk thermal conductivity of 20 watts per meter Kelvin. And also it's considered as a soft filler with most hardness of around 3. So the tests that have been conducted with the partnership with Metravib are based on epoxy 2K room temperature system. So we have decided to highlight some differences. So the first is only pure epoxy in red on the chart. And the other one is epoxy filled with our TIMal M3 ready to use multimodal ATH. So we have achieved 70% by volume filler content, which is pretty high, as we wanted to show some differences and also to highlight the performances in terms of thermal conductivity that could be achieved. So we will see after that. So here we can clearly see that the storage modulus, which is plotted, and tangent delta versus temperature increase. The field product shows that the storage modulus is much more higher when the epoxy is filled. So it's ATH act as a reinforcement agent. We can also see that the tangent delta could be used as a glass transition temperature determination. That's one way to measure it. The other way is also to take the TG onset, which equals to a slightly lower TG. But in any case, you can clearly see that it's not only a well-defined temperature where the thermomechanical properties drop down. It's really an area in between the range here of, for example, 50 to 90 degrees, I would say. So it could be also interesting for thermally conductive adhesive application where when you are looking for a battery replacement and adhesive dismantling, you can clearly see that you would better work at, let's say, 100 degrees, where the mechanical property of the adhesive itself are decreased. And the other partnership we have conducted with C-Therm is about thermal conductivity. So again, we have made some specimens unfilled epoxy, and in that case, we have made different specimens by increasing the filler content of TIMal M3. So on the table, you can see the benefit by increasing the filler content. And we have achieved for the higher amount thermal conductivity of around 3 watts per meter Kelvin. So again, this has been achieved only by using ATH. And on the right-hand side, I have put a small publication, which is relevant, I think, here in that case, where you can clearly distinguish 3 steps when increasing the filler content into your polymer matrix. The first one, you just increase slightly the thermal conductivity. In fact, your particles are just surrounded by binder, but individually in between the matrix. Then you increase sharply the thermal conductivity, which means the particles are now touching each other. So you are creating a thermal pathway. So heat dissipation is more efficient. And after the percolation threshold, then you have stage 3, where you have already created a lot of thermal pathway, and you are just creating some new channel, let's say. So I think, yes, I thank you all for your attention. You can see with the QR code, you have a link to access our web brochure for TIMal range of products. And we are open to sample. Should you have any sample request, feel free to ask. You have my mail here in the presentation. So thank you all, and I let Arya take the lead. Thanks.
All righty. Thank you to both Pankaj and Pierre here for that content. I'm just going to wrap things up with a little bit of an outro, some few housekeeping items, and then we'll be moving into our Q&A. Just regarding the Q&A, I see some questions posted in the chat right now. Again, please feel free to make use of that if folks definitely type in your questions, and we'll be addressing those here shortly. Okay, so from our side, again, these webinars are things we put on quite frequently. We do have a database of these collected for our past webinars on our website, as well as a tech library, which goes over quite a few different publications, different content pieces. If things like this were of interest, definitely feel free to take a look there for more content maybe related to this topic or other topics as well. Going forward, definitely give us a follow on LinkedIn if you're not already doing so. This is where we will be posting all of our upcoming events, blogs, webinars, and things of that sort. So if you want to keep up to date with us, give us a follow there. And just want to highlight a few upcoming events where C-Therm, Metravib, and Alteo will be at different locations, some different conferences coming up over the next few months. So the first one, the Battery Show Europe. This is coming up with a couple of weeks here, June 18th to 20th in Stuttgart, Germany. C-Therm, we will have a booth 6-G58, and Alteo will be at booth 8-G59. So if you're in the area, definitely feel free to stop by. We'd love to chat. The next one, the week right after that, C-Therm, we will be at the Adhesives and Bonding Expo, June 25th to 27th in Novi, Michigan. Following that, noting the ECCM 21, this will be a conference held in France in July. Metravib will be present there. The Battery Show North America, which is a little bit later, coming in the fall, October 7th to 10th in Detroit, Michigan. Again, similarly, both C-Therm and Alteo will have booths there. 3753 and 2853 respectively. And then last one that is currently scheduled is the Batteries Events 2024 in Lyon, France, October 16th to 18th. Alteo will be present there. So, if you're in the area, you maybe want to stop by, or you're going to be at these events anyway, definitely feel free to come check us out. Happy to have some conversations with you there. And with that, that brings us to the end of today's session. So we do have some time remaining. At this point, we will go ahead and stop the formal recording. I want to thank everyone for your attention and joining us here today. And for those of you who are